Okay, I did add some more stuff on D2L, a handful of things. Limiting reactions, identifying a limiting reactant, stuff on oxidation states, specific heat, reaction enthalpy. We can review some of that, but there's one more thing I'm going to add to this test that we'll have Monday. And I'll show you. This is based on Hess's law. Hess's law. Okay. So let me just write this as an example. So here's a reaction. Sb plus 3 halves Cl2 yields Cl3. You're given delta H equals 314 kilojoules. So at the end of class last time, I showed you the simplest way to do calculations with these. This is slightly different. It's based on Hess's law. Assume you have this reaction, and you're also given SbCl3 Cl2 is Cl5 delta H is negative 80 kilojoules. Okay. Cl3, Cl5. Now let's say you have this reaction. This is a different reaction. It looks similar. So you have these two reactions to work with, and you have this reaction that you're trying to find the delta H for. So here's a way you can find the delta H from these reactions. First look here and realize we need to end on the right side of the equation with SbCl5. So I'll look over here. This one has SbCl5 on the right, so that's where I want it. The Cl's, I need 5 halves of Cl's. This is actually set up too good. Maybe I should come back to that one because I need one that it's a better example. This is number 63 at the end of the chapter. Maybe I need. Yeah. Let me do number 65. I should click on that. Come back to this one. Do 5 at the end of the chapter. Okay. Hg2 Cl2 to Hg Cl2. And you're asked, what is the delta H for that? All right. And to figure it out, you're given some other reactions, Zn plus sulfur, delta H here equals negative. Is that the wrong one? Hg plus Cl. given this reaction, we're given another reaction, Hg plus GCl2 H2CL2 delta H equals. The point is, you can take these two equations with known delta H's, manipulate them such that they add up to this equation, and then you manipulate these numbers just the same to get this delta H. So that's the setup. All right, so this is our objective. All right, what I want to do is look up here and go Hg2Cl2. I need that on the left side. If you look down here, I've got Hg2Cl2. Here it's on the right side. And do notice, just notice this is HgCl2, not Hg2Cl2. It's a little confusing, but there's not a 2 here. Same here, there's not a 2 here. So this is different from this. So recognize that and realize what I'm trying to do is to get this on the left side the way it is up here. So what I can do here is I can flip-flop this around. So I have Hg2Cl2, and then I'll put these on the right side, Hg plus HgCl2. And when I do that, I multiply this by -1. I change the sign over here. So having flipped this one around, I'm now going to change this to delta H equals 41 kilojoules. So I've just manipulated equation number 2 and flipped it around backwards. Okay, now let's look at what we've got. I've got Hg2Cl2 on the left side. I need Hg and Cl2 on the right side. I have Hg. I still need a Cl2, and I need to get rid of this HgCl2. Okay. If we look up here, I've got my Cl2 that I need down here on the left side. So I'm going to get, let me point out where we are, HgCl2, HgCl2. So far I'm good. I've got an Hg there, and here's Hg. I know I've got 2 Hg, but I'm just looking to get the species to match up. So Hg, and I need Cl2 on the right side. I don't have a Cl2 on the right side. I have HgCl2 on the right side. Now let's use this equation. I've got Cl2 on the left side, so now I'm going to flop this one around backwards, like I did this one, so I can get Cl2 on this side. So let me do that real quick. HgCl2, that's this, and now I'm going to put Hg and Cl2. And since I flipped it around backwards, I'm going to change this sign. Delta H equals 224 kilojoules. So I'll flop that one around backwards. Okay. What do I need to do now? So this is just sort of like an arithmetic class where you could draw a line at the bottom and you just count everything down. But one thing you can do is you can cancel. If it shows up on the left side and on the right side, you can cancel it. So HgCl2, and there's only one of them, there's only one HgCl2, those will cancel, and I can just bring everything else down. So on the left side I have Hg2Cl2. On the right side I have 2 Hg's, so I'm going to write 2 Hg. And what do I have left? Cl2. That matches this. I just did all of that so I could match this. Do you see that? How I manipulated these two equations. All I did is have to flip them around backwards and everything added up. You see what I did? So the last thing to do is now I'm just going to add these together. 224 plus 41, delta H equals plus 41 is 5, 6. Okay. I just demonstrated Hess's law. Usually I don't describe all the excruciating details, I just do an example. So you're given two equations with their delta H. And yeah, the equations are picked out carefully so that you're able to solve. You could look up, these types of things are tabulated. Thousands and thousands of equations are listed in the Merck index in various places. There's probably an appendix with a bunch of these in it. But when you're given a problem like this, you're given an objective equation you're trying to match, and you're given 2 or 3 equations that you can play with to try to get them to add up to that equation. And then as long as you add up the math correctly, you get the delta H for the other equation. You follow that? So the only rule I've shown you so far is when you flip it around backwards, you change the sign. I'm not going to go back to that one yet. So let me just do another one. This was number 65 in your book. This one, that's a flip around. Let's see. Okay, I think this one will show. There's one other rule to show you as you do this type of thing. This is 66. I don't have any problems like this on D2L yet, but I'll get some up that we can review on Wednesday. Okay, your objective equation here, CO3, O4, 3CO, plus 2O2. Okay, that's what I'm trying to match. Here's the equations I'm given to work with. CO plus 1/2 O2. And this one's delta H. And you're also given 3CO O half O2. This is delta H. Negative 177.5. These are both in kilojoules. So you've got these two to work with, and this is what we're trying to make it add up to. First, notice CO3O4 is on the left side, and the only place you see CO3O4 down here is here. So I'm going to take this equation and flip it backwards. So it says CO3O4 gives me 3CO plus 1/2 O2. And then I'm going to change the sign on that. Delta H equals 177.5 kilojoules. So there, I just flipped this one around backwards and then changed the sign on the delta H. So now if I drew a line here, on this side I would have CO3O4. Kind of the problem is, if I add all these together, I'm going to have CO and 1/2 O2 over here as well. And I need those to go away. All right, the other rule, no, I told you that rule. 3CO, okay. Notice that CO, this is CO for cobalt and O for oxygen. COO doesn't show up here. I need that to go away. This is, in case it's not obvious, 3, C, lowercase o, uppercase O. I need the COO to go away because it's not up here anywhere. So here's another thing I can do. I've got COO here and COO here. What I can do is flip this one around this way, so I have COO on this side. So that's the first thing I'm going to want to do. So let me flip this one around. So being able to flip these around and work with them is part of the game here. So C, O, that makes 1/2 O2, CO. So there, I'll flip that one around, and now I'm going to change the sign. Okay. So if I took these now and added them up, I've got CO304 on the left, but I've also got some COO on the left that I don't need. I've got this COO on the right side, and I could make those two cancel if this had a 3 in front of it. So here's what I'm going to do next. I'm going to multiply through this whole side. Did I change that sign? Was that positive before? It was. So I flipped that around. I should have taken that negative off. Okay, my bad. All right. So what I'm going to do is multiply through this equation by 3, so I can have 3 here. What I'm saying is this times 3, this times 3, this times 3, which is 3 halves, and then this times 3. So this I'm going to multiply by 3. See what I mean? I multiply all the way through by 3, including this kilojoules. So 237.9 times 3. $713.7. Okay. Let's see where I am now. I need 3 CO, and things start to work out here because, like I said, the equations you're given to work with, they're going to work if you play with them a bit. I've got 3 CO here that's going to cancel. I've got 3 CO here, but I do need that. So now I've got this and this. 3 halves O2 and 1/2 O2. Three halves plus 1/2 is what? So if I add these up for the O2, what is that? 3 halves plus 1/2. It is 2. So I am going to end up with 2O2. Like I said, these just work out once you, because you're given equations that are going to work. You don't have to go look at hundreds of equations and find the ones you need. This will cancel. The 3CO comes down. Lord, I'm dyslexic. 3CO plus 2O2. CO304, 3CO, and 2O2, that does it. I changed the signs as I went, and I multiplied that by 3 as I went, so now I can just add these up. Better do it with my calculator. 713.7 plus 177, 891.2. So the whole point is, you're given an objective equation, you're told what would be the delta H for this, and then you're given some secondary equations to play with to try to make them add up to what you're trying to solve for. See what I did? You okay? So I want to put this method on the test too, the Hess's law. Let me give you another one. I have a couple more I can do. some in my PowerPoint as well. For these, it's just good to have a lot of them for practice. 66. Got one. How about this one is 64. Objective equation. That's what we're trying to match. And we're given also given ZNS plus 202 yields ZNS4. And that one's delta H is, and those are kilojoules. All right, so what can we do here? First thing to recognize, we need Zn by itself. We need O2 on the left, so there's O2 on the left. There's S on the left. There's Zn on the left. So these we want to keep. ZNS and ZNS, as long as those will cancel, which they do as it is, I think that's good. As it is, I don't think I have to do anything but just add them up. So let's add them up. All right. I've got one ZNS, one ZNS. I can cancel things. If I bring everything down, I've got ZNS 202. And over here I have ZNS4. Well, that's it. So this is an easy one. So then I'm just going to add these up. Negative 206 plus negative 776. Negative. Nothing after the decimal, 1 after the decimal, so I'm going to round to there. And it was negative. These were negative. That one I didn't have to manipulate. They just added straight up. Okay. And the first one, 63. In the chapter. Objective equation is SB plus 5 halves CL2 CL5. H question. And what you're given to work with is SB plus 3 halves CL2 gives SB CL2 CL3 balanced. Yeah, that's balanced. SB 3, and you're also given SB CL3 CL2, and of course you're also given the delta H's. We want 4 kilojoules. And this one is delta H, 80 kilojoules. So what do we want to do here? I need SbCl5 on the right side, so that's the way I want this one. The Cl's are on the left, there's an Sp on the left. I need the SbCl3 to cancel. I think all I have to do here is this trick. Which is the same as multiplying by 1. This is just so that when I add these up, I'll get 5 halves. That's why I did that. So this is 1. That's just a 1. That's just a 1. This is just a 1. So that times 1. And I think that does it. Because that'll cancel. I need that to go away because it doesn't show up there. So if I cancel what's on both sides, and then I would just add these up. 394. So the answer to this one is 394 kilojoules. Let's look at some of these that I have in my PowerPoint. I do have some like this to practice that I showed you last time on U2L. Just find some of these. Really work for these. This is law. See if I can solve these. Solve these. This one. Question is, what is that delta H? Given into H4 plus O2 plus N2 into here's the delta H. also given those are kilojoules. Okay, so this is the objective equation. There's no H2 up here, so I know this is what needs to cancel. Let's think here. I need that on the right side. Need that on the right side. So let's flip that one around. So N2 and 2H2. It helps to keep the arrow lined up for these. So that, and then N2H4 plus O2. And I flipped it around, so I'm going to make that positive 622.2. So those are the two equations I have now. So now that's on the right side. Got an H2, I need two H2s, and notice I've got three H2s here. Let's see. H2, 1 and 2, okay. Let's do this. Let's multiply, what is the H2O? Was that an H2O? Or huh? This was H2O? This was 2H2. Okay, so let's multiply from here by 2 to make the H2O go away. So this times 2 is 2H2. This times 2, that's a 1/2. So multiply that by 2, it's just 1. Multiply that by 2, and now I'm going to multiply this by 2, 285.8. So now this is still negative. 571.6 for that equation. Right. And if I just bring everything down, right, 2H2O cancels. I don't want the O2 up here, but notice that's going to cancel 2 now. And I'm down to N2 plus 2H2. Well, that's it. Yeah, that's it. I had H2 there before. That's it. That's what we wanted. That's the objective equation. So now I can just add these up. $571.6 negative plus 622.2. So delta H. Follow that? What else I've got? Let's try this one. Given this to work with H2O2. H2. delta H of -98.0 H2O2 H2O 1/2 O2. Joules, kilojoules. So what can we do? We need H2O2 on the right side. We need H2O to go away. We need H and O2 on the left side. So this one, so let's flip this one around. So H2O, 1/2 O2, H2O2, and then multiply this by -1, so it's going to be 98.0. So that's that one. So I'm going to multiply through here by 2. So the 2H2O will go away. So 2 times that is 2H2O. 2 times 1/2 is 1. 2 times H2O2. And then this times 2, what is that? 196. Is that right? 98 times 2, is that 196? It is?
It is.
Okay. So this is positive 196, this is negative 571.6. Alright. I'm going to go with this. I do have to fix something at the end, but I'm going to go with it as it is. 2 of those, 2 of those. Yeah. I'm just going to end up dividing by 2 in a minute. 2H2O, 2H2O cancel, and I'm down to 2H2 plus 2O2. I've got one O2 and another O2, so I've got 2 O2 here. And then 2H2O2. And then if I add those, $571.6, make it negative, plus 196. And I'm almost there. Do you see what I need to do to finish it? I've only got one H2 to one O2 to one H2O2. I'm just going to divide everything by 2 here. Which I probably could have saved myself a step, but that's just how my brain worked when I was up there. I guess I could have multiplied this by 1/2 and it would have done the same thing, and then I wouldn't have this step. But divide by 2, divide by 2, divide by 2, and now I've got to divide this by 2. I've really kind of added an extra step for myself. So there. You follow this? I'm going to do one more then. It's 3 equations with it. And we'll see if I can actually do it. So this is Hess's law. H3 plus 5/2. There's our objective. 2 H2O, negative 4, 3, 7. All right. So the only place we say see NH3 down here is there. And we need it on the left, so I'm sure I have to flip this one around. So let me try to do these in place. 2 NH3 into flip that one around, change the sign. It was into 3H2. So I do that, I erase the negative sign. I'm going to need 5 O2, and I've got 1 O2 there and 1 O2 there, so I'm probably going to have to multiply something by 4. Let's see. 6H2O. I'll multiply that by 2, that'll give me 4H2O. Yeah, so I multiply this by 3. That's what I think I'm going to do. That'll give me 6H2. H3. I know I need to multiply that by 2 to get a 4 there. So let me do that. 2 times 2 times 2 makes that 4. This is times 2. 4 of those. I've got to get 6 of these. Yeah, that'll work. So I'll multiply through here by 3. Still got this H2 to deal with. It's 2H2, alright. Still got that to get rid of. Alright. So I'm going to multiply through here by, what did I say, 3. 2 times 3 is 6. Times 6. 2 times 3 is 6. This times 3. What did that do? And 2 is not canceling. NH3. I need 4 NH3, so okay, you're going to multiply this by 2. So multiply that by 2, 4, multiply that by 2, multiply that by 2, I get 6. That's how I do it. I got too many oxygens. Anybody see where I'm going wrong? Those cancel. Those cancel. I get 8 oxygens. That cancels. What have I done here? I might just give up on this one. I probably won't do one like this on the test with 3 of them. Let's see where I got here. What cancels? What cancels? That cancels. I need that. I want that to cancel. So I've got 2 plus 6, 8 O2s, 4 NH3s, 4 NO plus 6 H2. bet that says 8. I bet that's an 8. If not, it's a 5. Is that balanced? 10 of those, 4. That's balanced, and this can be. Anyway, see?
You like 2 times 3 and you get your 6s.
Yeah, multiply here by 3.
So then your option would that be 3?
What did it say before?
So just like O2.
It just said 02? Yeah. Yeah, so that should have been 3, which would have made this 5. But anyway, if I did 2 times this, plus 2 times this, plus 3 times this, that would be the delta H. I think it's a little much for a test, but be able to do a couple of these slightly simpler ones for a test. I'll get some of these up on D2L for practice. And I'll upload this, it's just messy. There's one more with 3 of them there, that one's got 3. That one's got 3. Let's look at remember how to identify the limiting and the excess. This is reviewing now. You have this reaction. You've got 2 grams of silicone and 1.5 grams of N2. These are the ones I have online. And I bet it's the same example I did the other day. Look up here at the table. Silicon. Okay. Here's the amounts you're given of each one of these. Here's the balanced reaction. Which one is the limiting reactant? So of these 2, one of them is limiting and one of them is in excess. Do you remember where you start? Pick one. It helps to think that way. So I'm just going to go with silicon. Silicon is 28.09 grams, 1 mole. I did that wrong. You want to start with the grams you're given. And now I'm going to use this, but I want to flip it over. So I got this off the periodic table. So 1 mole and a sign. All right, now I'm going to use the molar ratio. I've got moles of Si up here, moles of silicon down here, and moles of N2. So I'm comparing the two reactants here. 3 moles of that to 2 moles of that. But now I've got this grams for N2. On the periodic table, that's for 1 nitrogen. This is for 2 nitrogen, so 28.02. This is the example I did the other day. I'm going to calculate that out, but the word need goes with what I'm calculating here. And the word have, this is what the problem told me I have. So I think it helps to sketch those in right there too, so you remember what you're doing. Certainly helps me. 2.00 times 2 times 28.02 divided by 28.09 divided by 3. We did this one the other day. That's how much I need. This is how much I have. Do I have an excess or am I limited? I need 1.33. Huh? So this is excess. That means silicon is the limiting reactant. And I'll say this. Do you remember why we want to know why that's the limiting? We were comparing the reactants. You're going to use the limiting one to predict products. That's the point. You figure out which one is limiting, and now you can predict how much product you're going to get. So it's another equation, but we're going to use limiting. In fact, we can actually use, we can reuse that much. So we have 2 grams of silicon, that's the gram per mole for silicon. We're going to compare silicon to the silicon nitride, which is, that's a 1 mole Si3 and 4. And we're going to need the moles per gram for Si3 and 4. Si, there's 3 of them. N, there's 4 of them. 28.09, 14.01. Those numbers are from the periodic table. All right. 28.09 times 3. This is 56.04, and if I add them up, so it's 140.31 grams per mole. And now I would put this label here. We're calculating the theoretical yield of the SF3 and 4. So 2 times 140.31 divided by 28.09 divided by 3. That's our theoretical yield. Do you remember what we do with the theoretical yield? if you were given this and you said you were given one more amount here, 2 grams of this, 1.5 grams of this, and let's say you got 3.15 grams of SN3 and 4. The theoretical yield the other day, I told you, that's the one that you got to do this long walk to find. The actual yield is very easy. It's always just given to you. That's the actual yield. That's not in this problem. I just added it so I could do a percent yield. So you've got an actual yield and a theoretical yield. It's actual over theoretical. I just made up this actual yield. And that'll give you a theoretical yield. Should at least change the amounts. Let's do this one. N2 and H2. That. And the amounts are 24.1, 6.58. So these are your amounts. And again, the question is, which one is limiting, which one is excess? Of the two reactants, one of them will be limiting, the other one will be excess. All right, N2 is so 14.01 times 2, and the 3 H2, so H2, 2.02 grams per mole. All right, and what do we do to start? Pick one. I usually just pick the first one. 24.1 grams of N2 for grams per mole for N2. One mole is 28.02. Okay, now the molar ratio between these two. Moles of N2 on top, moles of N2 on bottom, moles of H2 on top. You got 3 moles of H2 to 1 mole of N2. Now we got moles of H2 on bottom, grams per mole for H2, 2.02 grams of H2 to 1 mole of H2. And I'm going to write need this, and I have that. 24.1 times 3 times 2.02 divided by 28.02. That's it. I did something wrong. I guess it's okay. Good Lord. 6.58, 24.1. Oh. I did do something wrong. No, that's right. Okay. That's how much I need, and that's how much I have, so. Hmm?
Oh,
Well, H2 is, I don't have anywhere near as much as I need. I have 6.58. I need 519. Did I do that right? Let's double check that. 24.1 times 3 times 2.02 divided by 28.02. No, 5.21. Okay, good. 5.21. Is that right? Anybody following along here? Okay. All right. So I need this and I have this. So H2 is, I've got more than I need, so this is excess. N2 is limited. Now what do I want to do with the N2? Now that I know it's limited. The whole point of finding the limiting, it's not part of this problem, but the next problem set does this. Do you know what's next? Why did I find out which one was limiting? You're going to use the limiting to predict how much product. You're going to find your theoretical yield using the limiting. I didn't put a lot of those on there. But you can practice and make sure that you're able to do it. Reactions, limiting. Okay, I've got identify limiting, and I've got reactions, limiting. This one actually has you calculate the theoretical yield. So this one takes you the full route. Potassium, H2O. So let's do this one. Set it up. UK. Solid plus 2 H2O. Liquid. H plus H2. Gas. Aqueous. And you're told you have 12.3 grams of potassium, 2.6 grams of H2O. And this one doesn't say final limiting. This one says you might see problems that just say what is the yield. And it's the theoretical yield, and I guess I have to specify. I have to specify that because there's two products. So it's not the H2 we're looking for, it's the KOH. So specifically, what is the theoretical yield of that? To find the theoretical yield of this, we first have to figure out which one is limiting. Potassium is 3910 grams per mole. H2O, 18.2 grams per mole. All right. So if I just picked one, I'm going to start with K. And I'm going to go 12.3 grams of potassium, grams per mole of potassium. One mole is 3910. Now I've got moles of potassium. Potassium to H2O. It's 2 to 2. It's the same thing as just having ones there, but I usually just keep the coefficients when I do this. I think it makes it easier. 2O H2O. That's right. Mole of H2O. 1 mole of H2O is 18.02 grams of H2O. And this is need, and this is NO. .3 times 2 times 18.02 divided by 39.10 divided by 2. I need 5.66 grams of H2O. I have 2.6 grams. So H2O is limiting. I need 5.66. I only have 2, so this is limiting. That makes this excess. And now I'm going to use the H2O to predict the KOH. So I have to start over here at 2.6 grams of H2O. 18.02 grams of H2O. There's 1 mole of H2O. I'm going to have the moles of H2O on the bottom. And moles of KOH on top. Those are 2's again. 2 and 2. I am going to need KOH. 3910 for the K, plus 18, plus 16 for the oxygen, plus 1.01 for the hydrogen, plus 56.11 grams. So 2.6 times 2 times 56.11 divided by 18.02 divided by 2. You guys okay? I know these are kind of a long walk, but I did put in here a percent yield one. Yield. So question 3 here is percent yield. Let's do that. Percent yield. Percent yield. Yeah, there's only one product, so CL3. CL2 plus 3F2. 6 of those, 2 of those. you're told you have 4.39 grams there, 2.94 grams of F2, 4.67 grams of ClF3. What do we call this? Actual yield. We have to figure out the theoretical yield so we can find the percent yield. All right. CL2 is 35.45 times 2. So CL2 is F2 is 19, so 19 plus 19 is ClF3. ClF3. So 19 times 3 plus 35.45, 92.45. Okay. So I'm just going to pick CL2, 4.39 grams of CL2, grams per mole of CL2. Grams of CL2, 70.90. 1 mole. Now, moles of CL2. CL2 to F2. 3 F2s to 1 mole of CL2. Mole of F2. 1 mole of F2 is 38. I'm going to write need 4.39 times 3 times 38.00 divided by 70.90. So F2, is it excess or is it limiting? It's in excess. I have a lot more than I need, so this is excess. CL2 is limiting, and now we use CL2 to predict the product. And I can leave that much there. Moles of CL2 to 2 moles.
Wait, but if it's two.
Sorry?
Wait, it's two. You have 2.94.
Oh, you're right. That was limiting. What did I have here? It was 5 point something, wasn't it?
No, 7.06.
7.06. Okay, you're right. So this was. Okay. So,
Alright.
no. Alright, so we got to use F3. F2. So 2.94 grams of F2. Grams of F2. Moles of F2. 1 mole of F2 is 38. Moles of F2. Moles of our product. ClF3. 2 of these to 3 of these. moles of ClF3 to grams of ClF3. And it's 9245. And 2.94 times 2 times 92.45 divided by 38.00 divided by 3. Did I do that right? Anybody follow along there?
Yes, we do.
All right. This is going to be a little more than the actual yield, which I wonder if I did that on purpose. 4.67. Did you get 4.77?
I think it's been after you did
Let's
the
double check.
setup.
Let's make sure. 2.94 times two of those. 4.77. So actual over theoretical. And this is going to be a little bit over 100, which I know is weird. 4.77. Did that wrong. 4.67. Actual. Oh, no, this is fine. Okay, never mind. I have less actual. 4.67 divided by 4.77 equals that times 100. We get nice round 97.9%. Yeah, that's fine. Percent yield. So I know it's a long ball, but it's not that complicated, is it? Again, it's tedious. Okay. We can practice more of those Wednesdays. What words did I add here? Let's do.
Wait, you're supposed to do limited one, right?
Do what?
Not CO2, that's excess.
CLF3?
No, like if there you want an error from CLF2 to CLF3,
Here?
yes, sir. You have an error.
Oh. Yeah, that was before we figured out that I was wrong. We did it right though. We used F2, 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 2.94 F2. We did it right.
Okay,
I just didn't fix my error.
thank you. Just wondered. So you use the limiting one on here.
Hmm?
You use the limiting on here.
Yes.
Thank you.
You go to all that trouble to find out which one is limiting, so you can use the limiting one to predict the products,
And then
which is the same thing as saying final theoretical.
okay.
Good.
Thank you.
Good. What was I about to do? So let's look at specific. So I did specific heat last time. How much heat in joules?
And
No, I'm going to get rid of that. Heat. Calories is just another energy measurement. Iron block. This specific heat increases temperature. And let's see if I did these right here. All so it is specific heat. Specific heat specific to whatever substance we're talking about. Mass grams times delta T. That's the formula. This says, so that's the formula you want to use. This says, how much heat does it take? How much heat in joules must be added to 75.0 grams of iron with specific heat 0.449. I will give you the specific heat so you don't have to memorize it. I guess I should put the units here. Joules per gram per degree C. 75 grams. And our delta T here, it says from 25 degrees C up to 1535 C. So our delta T is final minus initial. Is that right? 1535 might seem real high, but this is iron. That's what's going to take to melt iron. And that's what the question says. You take it from 25 degrees C all the way up to its melting temperature. And you're just going to multiply these across. Grams cancel with grams, degrees C cancel with degrees C, you end up in joules. Now we see if I did it correctly. Times 75 times 1510. So I've got, my calculator says that's three significant figures. That's three. We actually have 4 there. This subtraction, nothing after the decimal, nothing after the decimal, so I calculated such that I have nothing after the decimal. That's actually 4 significant figures. But that's 3 and that's 3, so I'm really only keeping those 3. I think I wrote in there for the answer. I think I did a power of 10.
Yeah.
I didn't get creative with trick answers on this. That's what I've got over there, right?
Yeah.
No, it's, yeah, 508. Okay, how much will the temperature increase? So this one's just, this quiz just switches up where the variable is. How much would the temperature increase? That is delta T. 275 grams of water and I'll give you this on a test. fix that in there. Besides that, I'll give you this little test. I'm going to give you a sheet that's got lots of different, we call it specific heat values. So you don't need to memorize those values. So this, the problem gives you, it's 275 grams. For water, it's 4.184 joules per gram degree C. And we're solving for delta T. You don't even have to find temperature and final here. You just, what is the change in temperature? Notice this is in joules, and this is in kilojoules. If it were me, I would go ahead and go 36500 joules. So now both sides are in joules. 36500 divided by 4.184 divided by 275. And I get, so 31.7 degrees C should be in the answer. One more finding the specific heat. This time we're looking for C. Piece of unknown solid substance weighs 437.2. It requires 8460 joules. Temperature increases from 19.3 to 68.9. Now that we're solving for C, 8460 divided by 437.2 divided by 49.6. So I should say joules per gram per degree C, 0.39. Also have oxidation states and redox reactions and stuff on here. So you want to go back over those. And let me do this. What I did do on energy, that is enthalpy last time. So let me grab one of these. You're given that as a setup. What does it make of the change? Remember how to do this? Here's your students. Alright, let's start with the 78.2. And remember I said that this is similar to before. This is a summary form of 4 moles of NH3 to negative 1,267 kilojoules. That's one of the relationships that's here. Another relationship that's here is negative 1,267 kilojoules. That to 3 moles of O2. So that, then there's one for N2, negative 1,267 kilojoules, 2 moles of N2. And then for the H2O, it's negative 1,267 kilojoules to 6 moles. It's 2O. All right, for this problem, we don't need all of these. We only need this one. So I'm going to use this one. I need grams of H2O. I also need the grams per mole of H2O. It's 18.02 grams of H2O. There's 1 mole of H2O. And then I'm going to use this. I need moles of H2O on the bottom. I have that almost in the right spot. But I'm using this with negative 1,267 kilojoules over 6 moles of H2O. Now, keeping the sign here, it'll make this sign negative. $78.2 times 12.67, make it negative, divided by 18.02, divided by 6, negative 6, 3 significant figures. You guys okay? I don't guess I can bore y'all any more than this. Question?
Could you possibly explain, like I remember you talking about it in class the other day, but I didn't really understand like the reaction for people like what we're solving for. Like are we solving?
What this represents? This reaction with this negative sign, I did draw this. I didn't come up with a drawing for y'all for the test. But you start with the reactants at some energy, and you do this, products. Right. And this energy here, you have to put some energy in to make the bonds break to begin with, so that they can rearrange to make new bonds. So that's what this energy is. And then you end up down here, so it's this, the distance between where this is and where this is, that's the delta H. If the products are lower than the reactants, that means it lost some heat, meaning it's negative, meaning really the direction here is down. You start here, and then later you've come down here. This downward arrow is indicating negative, which means exothermic, which means heat came out during the reaction. It is, which is what I've got here. Since that's negative, that's telling you if you put these things in to react, if you stand here and put your hands in here, you're going to feel some heat come out. If that were positive, if you put the reactants together and you held on to the thing, you'd actually feel it get colder. But this one is exothermic, so it's coming out. I swear this book didn't say anything about exothermic and endothermic, so I'll put it on the next test, kind of these kind of details. I just wanted to be this simple calculation for y'all for this test. The other thing we did with delta H is where I started, where the Hess's law thing I was doing earlier. But the point is, in general, if you do this reaction with 4 moles of NH3 and 3 moles of O2, you will get 2 moles of N2 and 6 moles of H2O, and you will feel this much energy come out. But if you specifically put 78.2, or no, if you do the reaction such that you get 78.2 grams of H2O, that's how much heat will come out. So if you did it just right, where you produced 6 moles of H2O, I wouldn't have had to calculate anything. It would have been 1267, negative 1267. But since I didn't do it in this stoichiometric amount, I said 78.2 grams of H2O, whatever that is in moles. If I calculated that to find out how many moles it is, 78.2 grams divided by 18.02. So this that I got here that was negative 9, whatever it was, what was it, 931? What was it?
9.6.
916. If you put if you did this such that you produced 4.33 moles of H2O, that's how much you get out of it. But if you did it the full to the 6, then you would get 12.67. But this is specifying if you produced 78.2 grams of H2O, that's how much you would get out of it.
So basically you're just manipulating the formula.
Yeah. When you saw these that are set up this way, you saw it the way I'm doing it, and it'll tell you how much would come out for that specific situation. This is just balance the equation, give whole numbers for all the coefficients, and then you have this, what we call a standard sort of reaction. But then you can use that for any other amounts that you want to do it in. So if I said I needed, 700,000 kilojoules of heat, how could I produce that by this reaction? I can figure out how to produce that with this reaction, just by figuring out how much to put in to make it do it. So it's that type of calculation and the Hess's law calculation. And then for test 3, we'll do a little more about thermodynamics. We'll do more about exothermic and endothermic in that picture over there. I just want to leave the test kind of as is now. We'll just review Wednesday what we've got. You guys okay with what we've got? I'll get some Hess law problems together to practice on D2L, and we will put together a test out of that. You think this test is going to be easy?
Just big calculations.
It's a lot of calculations, yeah. I slacked on getting everything on D2L I wanted.